Vibrations, simple harmonic motion, what we term SHM, and pendulums. Here are your primary questions. You can pause and read through those, and I'm going to move on. First of all, a couple of definitions. A vibration is simply what we refer to as an oscillation in time. If you think of a spring with a mass on the end of it moving up and down, that is going to be an oscillation just in time. In space, it's only moving in a single dimension, so we don't have to worry about it. This is what we call a vibration. When we talk about the temperature of objects, we're talking about the vibration of the molecules moving back and forward, and that's what we're talking about for that. So that's a vibration. When we talk about something that being periodic, if you think back to the periodic table, there are repeating characteristics, and when we talk about periodic in physics, we're talking about a repeating motion. So that's for us periodic. A pendulum we can simply define as an object that is attached to a pivot point so it can swing freely. We're going to start with pendulums because they're easier to talk about for simple harmonic motion. Now, this pendulum is subject to a restoring force that will accelerate it towards an equilibrium position. And if we think of a pendulum, that equilibrium position is going to be where it's hanging straight down and it's at rest. And we're going to talk a little bit more about that in just a moment. Now, when the pendulum is displaced or moved from this place of rest, the restoring force will cause the pendulum to oscillate about the equilibrium position. If you think of any pendulum that you've used or made before in the past, when you would bring it up a certain distance and let it go, it would move back and forth, back and forth. And the reason for this is because as it moves away from its equilibrium position, there's going to be a restoring force going back towards the equilibrium position, which keeps changing as it moves from side to side. So here are some other new terms. We can simply define the equilibrium position as where there's no net force, and I'm going to focus on that, no net force exerted on the object. So this is its rest position. When we say no net force, we're not saying that there aren't any forces acting on it. In fact, if we had our pendulum with a mass on it, we would know that we have a gravitational force acting down, and we have a tension force acting up. So there are still forces acting on it, but if this is at rest and it's in its equilibrium position, we know that the sum of these two forces, the net force, is zero. Displacement, this is the distance measured from the equilibrium position. For us, it's typically going to be easier to measure in degrees rather than in meters, where we would have to be measuring the arc distance, and that's not going to be fun for us. So we typically stick with degrees for us, for pendulums. And the amplitude is simply the maximum displacement. So displacement, just how far it is from the rest position. The greatest displacement is your amplitude. And now when we talk about simple harmonic motion, and this is when we also talk about simple harmonic oscillators, this is where the restoring force is directly proportional to the negative displacement. And all that tells you is if we have a displacement to the right, we have a restoring force. Let me see, put that as a D. We have a restoring force to the left that is directly proportional to that displacement. So that's why it's going in the opposite direction. That's why we say the negative displacement. So when an object is doing this, it is undergoing simple harmonic motion, and when that object is undergoing simple harmonic motion, we call it a simple harmonic oscillator. So SHO is the term that we use for that. Here's where things get a little bit more complicated. A pendulum is not a true simple harmonic oscillator, and it's because of the directly proportional statement. And if we think of what a directly proportional relationship is, it means that as one variable is going up, the other variable is going up at the same factor or at the same rate. As one decreases, the other decreases also at the same rate. The thing is with the pendulum, the restoring force is due to the weight of the object that is attached to the pivot. So we have our string, we have our mass at the end of this, and that mass has a gravitational force acting on it, going straight down. From there, the component of that is contributing to the restoring force is this one right here. It is the perpendicular component in this particular case, and this is mg sine theta, where mass times gravity, that's the force, and it's times the sine of the angle of the displacement over here. So it's not directly proportional. The restoring force is not directly proportional. It is proportional to the sine of the theta. And this is why a pendulum is not a true simple harmonic oscillator. But for us, at sufficiently small angles, so at small thetas, it is a very good approximation and a very good way for us to learn about simple harmonic motion, because at the small angles, it is a very good mimic of simple harmonic motion. And this is a quick diagram or animation about the acceleration and velocity vectors of a pendulum at different displacements. And what I want you to look at is I want you to make some observations, and I want you to write down some of the things that you notice. We are going to discuss these in class. What do you notice, or what are some observations about the relationship between the velocity and acceleration vectors? What happens to them at different parts in the motion? What are your observations? Next, a couple of more terms. We have period and frequency. These two terms are related to each other, but you have to be very careful with the two. Period is the time it takes for the mass to complete one cycle, whereas the frequency is the number of cycles completed in 1 second. Typically, we use 1 second for here. So the period is going to be measured in time, and our default unit is going to be simply the second. You can think of this as seconds per cycle, if that helps. And frequency, the number of cycles per second, so you can think of that as cycles per second. And the term that we use for this is the hertz. So that is the unit for our frequency. When we talk about cycles per second, this is going to be in hertz. So 1 hertz is 1 cycle per second. And if you look at this animation, you can see a sinusoidal wave being formed by this mass. And if we look at the peaks, we can see that this is going to be about 1 full cycle, so between 2 identical peaks. And the time it takes to do that 1 cycle, that's the period. And how many times this goes up and down, so down and up, to produce 1 full cycle, it's going to be the number of cycles per second. And that's going to be the frequency. So if we know that period is seconds per cycle, and frequency is cycles per second, what can we say is the relationship between period and frequency? And what do you think the equation for period and frequency is going to be? Try to answer those. We'll talk about that in class. Now for the Pendulum Lab. There are going to be 3 parts to this. You are going to have 3 data tables made in Excel, and I'll help you with that in class. You're going to be measuring 3 different variables versus the period. You're going to do period versus mass, so you're going to be changing the mass. You're going to do period versus string length, changing the length, and then you're going to do period versus the amplitude, and you're going to be, again, measuring this in degrees. What you're going to be doing is trying to figure out which of these 3 variables influences the period. Now, what you also want to be thinking about is, as you are changing one of these variables, you need to keep all of the other variables the same. With your data table, in the top of the data table, you want to state what your conditions that you are controlling are going to be. If you're setting up the mass to see if that's the influence, you want to make sure your string length and amplitude are the same for all of your different trials so you don't confound your results. Now, the way we are going to be setting this up, and let me move this off to the side. Actually, let me just go and delete it. You are going to have a setup that looks something like this as a side profile, and this is going to be your table. And there's going to be a vertical board attached to a piece of wood, and it's going to be a board that has a hook, a straight out hook, well, an attachment that goes to the pegboard. And from here, what you'll want to do is you will want to set up the string and tie it off on 2 parts so that when it hangs down with a mass attached, the mass is hanging in the middle of a V. And the reason for this is that this will restrict the motion of your mass to move only in one plane so that you have a lower percent error. Now, what you have to be careful of, though, when you're doing this, when you're measuring your string length, it's not going to be the total length of the string. It is going to be the bisect of that. So it's going to be measuring from the center down, the bisect of that V. And remember, change only one variable at a time. You want to record all your variables. For this, you want to make sure you have multiple trials. You want to make sure that you are as accurate and precise as possible. And to help you with that, you want to measure more than one period at a time. I highly recommend for you to measure 5 periods. And what that means is, if we look at this from a different perspective, so if this is our pivot point, so we're looking at this straight on, and let's say, for example, that you pull it back at this angle, so this is going to be your theta here, that's your theta. When it moves to this side, and then moves back to the original position, that is 1 cycle. And the time it takes to do that is 1 period. To reduce your error, you want to allow it to move back and forth, back and forth, back and forth, a total of 5 times, so that you can have a smaller percent error, because you're going to be measuring the time with timers that you're doing this by hand. And that's how you want to reduce your error. You'll be doing this in class to record your data. Eventually, you'll put this into an Excel spreadsheet, and then you're going to be graphing these. And once you look at your data, you should have a pretty good idea of which one influences the period. And then I'll explain what to do more